All right, we're about to go on a little journey. We're going to follow a single ray of light. And believe me, it's going to show us some of the coolest, most fundamental secrets about how our world actually works.
It all starts with a simple question I bet you've asked yourself before. Go grab a shiny spoon, look into the part you eat from, and what do you see? You're upside down. Why is that? Well, the answer reveals the secrets of how light truly behaves.
So, to get to the bottom of this whole spoon mystery, we have to start at the very beginning. We're going to trace the actual path that light takes as it travels through the world, bounces off of objects, and creates the images that we see.
Okay, so let's think of this as a story in three parts. Act 1, the predictable path. This is where everything is nice and simple, a world of straight lines and rules that are easy to follow. It's all about how light behaves when it's on a straightforward course. First things first, what even makes something visible? I know it sounds super obvious, but let's really think about it. If you're in a completely dark room, you see nothing. You flip a switch and boom, the world appears. So what is actually happening in that moment?
Well, it's really a two-step dance. Light from a source, like the sun or a light bulb, hits an object. That object then bounces the light back, and when those reflected rays enter our eyes, our brain processes it as an image. No reflection, no vision. It's as simple as that.
And this bouncing action? That's what we call reflection. Just think of it like a super fast tennis ball hitting the wall. It comes in, it strikes the surface, and it bounces right off. That's the basic principle we're working with here.
But here's the thing, this bouncing isn't random at all. It follows two very strict, unbreakable laws. First, the angle the light ray comes in at is the exact same angle it goes out at. And second, the incoming ray, the reflected ray, and something called the normal, which is just an imaginary line at a right angle to the surface, they all exist on the same flat plane. It's perfectly predictable.
Right, but the world isn't all flat surfaces and straight lines, is it? So let's move on to Act 2 and see what happens when things get a little curvy. This is where light starts doing some really interesting, unexpected things.
And this, of course, brings us right back to our spoon. Those simple laws of reflection still apply, 100%. But on a curved surface, the outcome is completely different. So how does a simple curve change the whole game? The spoon is the perfect tool for this. The inside, the part that's curved inwards, is a concave surface. It takes light rays and pulls them together, or converges them. The back of the spoon, the part that bulges out, is a convex surface. It does the opposite. It spreads the light rays apart, or diverges them. And here's a brilliant way to see the power of a concave surface. If you take a concave mirror and reflect sunlight onto a piece of paper, you can focus all of that light and energy into a single, tiny, intensely hot point. If you hold it there, the paper will actually start to smoke and burn. So what's happening is the curved mirror is collecting all that sunlight from a wide area and concentrating it. That super bright spot is called the focal point. And here it is. This is the solution to our spoon mystery. When the light rays bouncing off an object cross over at a focal point before they get to your eyes, the image gets flipped. That's why you appear upside down. But reflection is only half the story. See, light doesn't just bounce off things, it also travels through things, like water or glass. And when it does that, another strange thing happens.
You've definitely seen this before. Think about looking into a swimming pool. The bottom always looks shallower than it really is, doesn't it? Or what about when you put a straw in a glass of water and it looks like it's broken right at the surface? That's not an illusion. It's a property of light itself.
This whole phenomenon is called refraction. All it means is that when a light ray travels from one medium, like air, into another one, like water, it actually bends and changes direction. It's this bending that makes the bottom of the pool seem so much closer than it is.
So why does it bend? It's really simple. Light changes speed. Light travels at different speeds in different materials. So when it crosses the boundary from a fast medium, like air, to a slower one, like glass or water, that sudden change in speed forces it to bend. Okay, so we've got light that bounces predictably and light that bends when it changes speed. For our final act, we'll see how humanity took these rules and learned to control them, to literally shape the path of light for our own uses.
And the key to controlling that bend is the lens. A lens is just a carefully shaped piece of transparent material, usually glass, that's designed to bend light in a very specific and very useful way. It's the technology behind everything from your glasses to giant telescopes. And just like with mirrors, we've got two main types. A convex lens, which is thicker in the middle, converges light to a focal point. That's your classic magnifying glass. Then there's the concave lens, which is thinner in the middle, and it does the opposite. It diverges light, which is really useful for things like correcting nearsightedness.
And just to put this all into perspective, light travels in a vacuum at an incredible 300 million meters per second. It's the change from this absolutely mind-boggling speed as it enters different materials that allows all of refraction and therefore all lens technology to even work.
We can even measure how effective a lens is. The power of a lens just describes its ability to bend light. A lens that has a short focal length, meaning it bends light very sharply to a very close focal point, is considered more powerful than one that bends light more gently.
So, there you go. From the simple reflection in your bathroom mirror to the complex refraction happening in your eyeglasses, these two fundamental principles, reflection and refraction, are constantly at work all around us. Understanding them is understanding how we see and manipulate our world.
Which leaves us with one final thought. We started this whole thing by just following a single ray of light, and it led us to understand mirrors, lenses, and the very nature of vision. It makes you wonder, right? By mastering the path of light, what else can we bring into focus?